Hello everyone, today I want to tell you about Biconnectivity, finding Biconnected components in an undirected connected graph. At first, let's define this term. In graph theory, a Biconnected graph is a connected graph, meaning that if any one vertex were to be removed, the graph will remain connected. In other words, any two vertices have at least two non-intersecting paths. Therefore, a Biconnected graph has no articulation vertices. And how can we find these Biconnected components or define that the graph is already Biconnected? So we use the algorithm. And here is the quite short, really short description of this algorithm of how does it work. So we build a depth-first spanning tree according to given graph using DFS. Edges which weren't added into tree are back edges. And analyzing back edges is the way how to recognize Biconnected components in given graph, or point out the graph is Biconnected. Want to go deeper? Here's the lemma. Let G be a connected, undirected graph, and let S be a depth-first spanning tree for G. So then, vertex A is an articulation point of G if and only if either. The first, A is the root and has more than one son. The second, A isn't the root and for some son S of A there is no back edge between any descendant of S, including S itself, and a proper ancestor of A. Well, let's prove it. So it's easy to show that the root is an articulation point if and only if it has more than one son. And here is an example. In this picture, we have two graphs, and let's proceed DFS on both of them. Let's start with this vertex. Since we started here, this vertex is going to be a root of our DFS spanning tree. So we go here, then here, here, and here. So we finally get this point. And what does it mean? It means that this edge won't be included in our tree, because in either way we'll have a cycle. It's not a tree. So it means that these vertices will not be connected by this edge. And we continue proceeding DFS, we go here, here, and we finish. Anyway, as a result, we have this vertex being a root without two sons. It has only one son in our DFS tree. This vertex is a son of this vertex. And this node isn't an articulation point. It's quite obvious, because if we want to get from this vertex to this, we may use this path, which contains this vertex, but also we may use this path. And according to our definition, we have at least two non-intersecting paths to get from this vertex to this vertex. Let's go to this graph and start proceeding DFS algorithm on this one. So we also start here. This vertex is going to be our root. We go here, here, then here, here, and we stop. DFS back to this vertex, to this, trying to find another unvisited vertex. We finally return to our root and continue proceeding algorithm exactly to this vertex. We get it. We get this vertex, then this, and we finish proceeding our algorithm. And what do we have as a result? As a result, we have a DFS spanning tree. This vertex is being a root and have two sons. So, according to our first statement, to our first condition, this point is an articulation point. It's obvious, because if we want to get from this vertex to this, we may use only this path. We just know any paths. So this is an articulation point. The first condition is true. Well, suppose condition 2, this condition, is true. Let f be the father of A, and each back edge goes from a vertex to an ancestor of the vertex. It's just a quite obvious property of back edges. There's nothing special. This any back edge from a descendant V of S goes to an ancestor of V. In this picture, in this picture, we can see the description of the proof for the second part of this lemma. And by the hypothesis of the lemma, the back edge cannot go to a proper ancestor of A. Hence, it goes either to A or to a descendant of S. This every path from S to F contains A, implying that A is an articulation point. Let me explain what I've just said. So we have F being the father of A is the father of F of S, and V is the descendant of S. And according to the second condition of our lemma, there is no any back edge between descendants of A and its proper ancestors. This every path from F to S contains A. Therefore, A is an articulation point. So we've just proved this lemma from one side. Let's do it from another one. Here we have two pictures. Let's pay attention to the first one. And what do we have? Let A is an articulation point. And what does it mean? It means that any path between any two vertices, let X and Y, contains vertex A. And in first case, let X be a descendant of A. Y isn't descendant of A. Let V be a descendant of A2 as well as X. And we have a back edge, VW. And when we start here, we go right here, and then we get the V. And using back edge, VW, we get this vertex. And this vertex, I mean W, is a proper ancestor of A in this situation. We go here and here. We get vertex Y, and we've just found a path between X and Y which doesn't contain A. Contradiction, because A is an articulation point. So it means there's no any path between X and Y which doesn't contain A, but we found one. So move on. The second picture is the second case when X and Y are both descendant of A. And here we have vertex S prime and vertex V prime, vertex W prime. And of course we have a back edge, V prime W prime. And what can we do there? We may also start our path right here. From X we go here, then here, and using back edge VW we get to the first proper ancestor of A. Then we up to W prime, and using back edge W prime V prime we go right here. We go here and we get Y. It means that we just found a path between X and Y which doesn't contain A. And know the contradiction, because A is still an articulation point. So we've just proved this lemma and we may go on. So let's continue. This algorithm works based on a previous lemma. Now let me define a function low of V. It's lowest number of vertex, where backedge from V goes. To define this function, it's convenient to number each vertex in order of DFS approaching to this vertex. The pre-order numbering implies that if x is a descendant of V and xw is a backedge such that w is less than V, then w is a proper ancestor of V. Thus, by previous lemma, if vertex V isn't the root, then V is an articulation point if and only if V has a son S such that low of S greater or equals to V. Well, it's probably the main idea of this algorithm, and we may go on. Let's talk about complexity. It's really important stuff when we talk about algorithms. So the time complexity of this algorithm is O of E, whereas the space complexity is O of E plus V, whereas E is the number of edges in our graph and V is the number of verges. So why is it so? Let's start describing time complexity. Why is it so? Well, algorithm checks every edge, then puts this edge to the stack, and then subsequently pulls this edge out. So it means the algorithm made approximately E operations. So the time complexity is O of E. It's quite clear, I think. But if we are talking about the space complexity, it's a bit tricky. Because, well, from the one side, algorithm keeps every edge in a stack. So we spend O of E memory, of course, yeah, it's true, but the algorithm is a kind of recursion. So it means that we have to keep every calling in a call stack. And in the worst case, we'll have V method calls in our call stack. So therefore we have to summarize both complexities and we will get O of E plus V. Well, it's very important. It's very important considering that the algorithm is a kind of recursion. Where we can use this algorithm in a practical ways? Well, we may use it to analyze different systems represented in undirected graphs for detecting weaknesses or elements on which the system is highly dependent. These elements can be articulation points. So we can see that this algorithm is quite useful in our lives because there are lots of systems which we can represent in undirected graphs. So I think literally every graph algorithm is appropriate to solve some problems which we may face in our lives. Here's the literature I used, the design and analysis of computer algorithms. It's a classic book by Alfred Aho, John Hopcroft and Jeffrey Ullman. I recommend you this book to read highly, highly, highly. And here's the algorithm itself. It's written on C#, my favorite language. So, here's the algorithm. Well, it starts from marking the current vertex as visited one. Then we mark the DFS ID, we numbering this vertex, and we define a low function meaning. At first, it's similar to DFS ID. Then we're gonna find the first unvisited adjacent vertex to this one from which we've just started. And if we've successfully found, this node will may continue. So we have an edge right here, node and adjacent node. We push to our stack of edges this one, marks current node as a dead for its adjacent node, and start producing our algorithm for adjacent node. After leaving this method, we check this. If it is true, we proceed this part of this algorithm. After that, we change low meaning for current node again, choosing the lowest meaning between the current low and adjacent vertex low function meaning. But what algorithm will do if adjacent vertex is already visited? It will check this condition. If current vertex dead isn't adjacent node, it means that we found a back edge. So we change our current node low meaning again by taking the lowest between these two meanings. But also, because our graph is undirected, there is no difference between 1, 2 or 2, 1 edges. So we have to check if this edge is a real back edge. It's back edge in this situation only if the start node index is higher than the finish node index as well. So, and only in this situation we push this edge to our stack. And by the way, yeah, let's talk about this. And if this condition is true, it means that the algorithm found a Biconnected component. It creates a list of edges where we will put our edges, and then the algorithm pops out every edge till the current edge where the algorithm is standing. After that, we add this list to our super big list of all results. And after algorithm finish proceeding his operations, we return our result and the number of iterations, because my task was to analyze the results and build the graphics. Oh, let me show these graphics. Where's the graphics? Here we go. And here we can see we have 4 lines. They're absolutely same. Well, at first it means that the algorithm is actually linear of a number of edges multiplying by 3. But 3 is a constant, so it doesn't matter at all. And by the way, it's working quite good no matter which graph is given. Biconnected, not biconnected, and even random graph. It works stably. There's no any problems with analyzing different types of graphs. The time complexity will be the same. Thank you for your attention. Goodbye.